Good morning. I would like to start by telling you a story about something that happened just a few days ago. It turns out that a Chinese company had just released a new large language model, which is called DeepSeek 3. And it surprised everyone because it's very competitive with the latest ChatGPT version, which had been trained by OpenAI at great expense in competitive tests. It performed very, very similarly to this ChatGPT. And the white paper that accompanied the release of DeepSeek 3 said that the Chinese company had managed to train this model in just 2 months at a cost of $5.5 million, compared to hundreds of millions of dollars for OpenAI. So everyone was scratching its head, not understanding what is going on. How can you train a model so cheaply, so quickly? And then somebody had a clever idea of just asking this DeepSeek model, who are you? And the answer was, I'm ChatGPT. I'm a large language model trained by OpenAI, et cetera, et cetera. So totally unrelated to this, I'm going to talk about whether it's possible or easy to steal a network by interacting with it. So I'm going to talk about a number of consecutive papers which were published last year and are being submitted to conferences this year, which solves this problem. And I'll try not to be too technical because I want to give you the essence of the ideas. I know that most of you are not computer scientists or mathematicians, but I hope that with a lot of pictures, things will become clear, at least on a grand scale. So for those of you who have never seen how deep neural networks operate, they are extremely simple. The only non-linear operation, the only operation which is a bit clever in that deep neural network is a function which is called ReLU, rectified linear unit. And it is very simple. It's a mapping from one real number input to one real number output. If the real number input was negative, then the output is 0. If the input was positive, then the output is the same as the input. So it has this shape. It is flat at 0 for negative numbers, and then it becomes slope 1 linear function for positive values. And that's the only source of nonlinearity which makes things complicated. So in addition to this nonlinearity, the ReLU, the way the network operates is the following. You have a bunch of real numbers as an input. I'm talking about plain vanilla kind of deep neural network. Later on, it becomes more complicated in order to deal with words other than numbers, etc. But the simplest version is you have a bunch of real numbers at the input. You mix them linearly. That's the linear mapping A1. And A1 has parameters which are the secrets. This is what I'm going to steal. And then you go through this nonlinear ReLU layer, which basically changes every negative value to a 0. And then you again mix all the values linearly with another bunch of secret numbers. And then you go through the ReLU and so on and so on. At the end, after many layers, you get a bunch of real valued outputs. And that's what the deep neural network produces. That's the whole thing. So the problem we are going to consider is how difficult is it to extract all those secret parameters which are in the linear mappings. And this, if you think about it, this is the problem of solving a system of nonlinear equations over deep neural networks. You are given inputs and outputs, and you have to find all the parameters which are mapping it. If it was a system of linear equations, we have Gauss elimination, we know how to solve it. But here we have all this nonlinear function, and it's not obvious how to solve a system of equations over such ReLUs. So this had been an open problem for many years. Actually, it's a 30-year-old open problem. Some of the earliest results were by Rivest and Blum in '93. They showed that the problem is NP-hard, but in a particular way. If somebody is giving you a particular, carefully chosen input and its corresponding output, and is also forcing you, for this input, you must produce that output. You can encode complicated NP-complete instances of NP-complete problems, and therefore show that we have no chance of solving it in this scenario where you're not really allowed to interact and ask your own question. Somebody is forcing you to ask the particular questions, and these are the only answers you get. Then the problem is very difficult, but if you can interact and choose your own questions, it's not clear what's happening. And there's also another famous mathematician, he's actually a field medalist, Charlie Pfefferman, and he also showed that in principle, the parameters are unique up to certain symmetries if you are given access to the whole input-output relationship. So given kind of the full description of the deep neural network, how any possible input, what is the corresponding output, then you can get then the parameters are uniquely defined, but it didn't talk at all about how difficult it is, whether it's polynomial time, exponential time, etc. So I'm going to show you a polynomial time attack on it, and I'm following ideas which had been developed in many previous papers along the way, but they were all stuck at exponential running time. And this is, I'm going to show you for the first time that it is possible in a polynomial number of questions and answers. What is polynomial? It means that it grows with the number of secret parameters or the number of neurons in the network in a way that is manageable. It goes like quadratic in the number of neurons rather than being exponential in the number of neurons. And we have experimentally verified our attack that it's not only theoretical, it's also practical by actually taking a deep neural network with 8 layers, about 2,000 neurons, more than 1 million secret parameters, and we extracted all of it in less than 30 minutes. So it's working extremely well even in practice. Okay, so to a cryptographer, everything looks like a crypto system. So I want to show you that actually this structure on the left that I showed you before is very similar to a structure that cryptographers are well aware of, and this is a block cipher. A block cipher is taking a bunch of input bits, not real values, but bits, zeros or ones, and it is linearly mixing them. In order to encrypt the data, you are linearly mixing the bits, modulo 2 technicality, and then you pass them through a nonlinear function, which is called an S-box, which is, plays a role similar to the nonlinear ReLU function. And then you again linearly mixing it, and again going through the nonlinear function S, etc., until you get a bunch of output bits, and they are called the encrypted value, the ciphertext. And the problem is, given many inputs and outputs of this block cipher, can you find the secret keys which are embedded in those linear mappings? So you see that there is a lot of common structure. Okay, I'll skip this. And now I'm going to tell you how we are going to attack the problem. We are going, just like we are attacking crypto systems layer after layer, finding the first secret key, then the second secret key, which is embedded in the second layer, etc. Here, I'm going to find the parameters in the first linear mapping. After I complete this task, I'll find it in the second linear mapping, and so on. So where am I at an intermediate stage in this process? I'm now at layer number I. I assume that layers 1 up to I minus 1 have been completely solved. You know all the parameters, so you can run it yourself. It's a function which is known. That's the input function fi minus 1. It combines everything up to the current layer, and you know exactly how to run it. Then there is the current layer, which is still unknown, but that's what I'm going to work on. So the linear mapping is the Fi, followed by the nonlinearity sigma. And then there are additional layers, because I'm still in the middle of the attack. And this is the output function, and I know nothing about this output function. OK, so I'm now going to do the following. I'm going to define the notion of a critical point, which will play, of course, a critical role in the attack I'm going to describe. A point in the input space, a particular vector of inputs, is called critical if it is just at the point at which one of the internal ReLUs is about to change from negative to positive. So this is where a bend is located. And I can assume that if I am at a random location in the input space is very high dimensional. There are thousands of inputs corresponding to the various pixels of the image or whatever you present to the deep neural network. I can assume that when one ReLU is changing, all other ReLUs are either on the negative side or on the positive side. It's very unlikely that exactly at that point, several ReLUs will change their direction simultaneously. OK. So critical point is where some ReLU, I don't know exactly where, is going to switch sides. And when we move in the input space, we explore it by going in a certain path, then we are going to cross many critical points. So if I start from an image of a cat, and I go towards an image of a dog by changing the values of all the pixels in that image, at some point, one ReLU will click to the other side. And then I continue along my path, and another ReLU is going to click. So I'm going to encounter thousands and thousands of such changes of ReLUs from one side to the other. And the point I'm making is that this is extremely useful. Why? Because it is leaking internal information about what is going on in the middle of the deep neural network. I suddenly know that at a particular point, the value of the vector, the value of the output of a linear mapping was exactly 0 when it entered into a ReLU. And when it's 0, I can write a linear equation. And if I go in multiple directions in the input space, I encounter many ReLUs, I'm going to start writing more and more linear equations that a particular linear combination of internal values is equal to 0. And once I collect enough linear equations, we know how to solve linear equations. So that's the big picture. Of course, we are going to encounter many, many difficulties along the way. OK, so here is the picture of what I just told you. Because the only source of nonlinearity is the ReLU, the input space is actually divided by the critical points into small regions. Let's call them cells. Here is my starting picture of a cat. And this is the ending picture of a dog. And when I say that I connect them by a straight line, it means that the value of each pixel is slowly changing, continuously changing between the value of that pixel in the image of the cat to the final value of this image in the picture of the dog. So each pixel by itself is changing continuously and linearly between an initial starting value and the final value. So I'm moving in a certain straight line direction within input space. And I can think about it as I have one parameter, which is how far am I on my journey from the initial image to the final image. Let's call it t, time. When time is 0, then all the pixels have their value in this image. And when time equals 1, all the pixels have their final value in the picture of the dog. Now, the point is that the straight lines here are the critical points where some ReLU had switched from one side to the other. Unless a ReLU switched sides, everything is just a composition of linear mappings. On the left side, a ReLU is a linear mapping. On the right side, ReLU is a linear mapping. All other things are linear. So in the small vicinity of any non-critical point, the behavior is totally linear. But when I move along my journey and reach this critical point, suddenly a ReLU click to the other side, and the whole linear behavior now becomes a different linear behavior. So I have one linear behavior in this part of my journey, and then another linear mapping in this part of the journey, etc. So I'm switching through thousands of linear behaviors. Now, how does the output look like? Now, I have only one input parameter, not the millions of input parameters we usually think about. The one parameter is my time. So this is the x coordinate. And the y coordinate is, for example, what is the first output or coming out of the deep neural network. So I told you the story that unless I hit a critical point, I'm behaving linearly. So this is the value at the original image of the cat. And as I'm moving initially towards the dog, the output is not going straight in that destination. It is going up. I hit a critical point, and suddenly it goes down quite steeply. And then I hit another critical point, and now I'm in a new regime, a new cell, a new linear mapping. So now it is going down, but slowly. And I have this zigzag shape. And every time I change direction, and I can easily explore the output, since I'm allowed to ask any question, put any input, I can see the point at which I was going up, and now suddenly I'm starting to go down. So I can identify those turning points, and therefore, I know that some ReLU internally in the network had switched. OK. So the next thing, you see, a cryptographer always tries to find small advantages which allows him to, or her, to put her foot in the door, and this is an initial crack. And then you try to widen it until you break open the whole thing. So the next thing that you have to convince yourself is that the value at the output depends on everything, on the earlier layers which are already known, at the current layer that I'm exploring, trying to understand, and at all the output, because the output is also a linear mapping, the output function, totally unknown to you, but locally, in the vicinity of the critical point, it behaves linearly, and therefore, it can only change the slope. It cannot create a new kink in the behavior of the function. So if the kink belongs to a ReLU, which is in the current ith layer, no other kinks are going to be created by the later layers from I+1 until the very end. They only change the slope of the output. So the location of a ReLU that flipped at layer I is not affected at all by all the linear maps which are in the later layers. So it only, if I look at not at the value, but at the coordinate x of the kink, then I can use only things I already know from the input function, the current layer where the kink happened, and I can ignore all the other layers which are coming later on. And that's a crucial observation, which allows me to work layer by layer and understand what's going on. OK, now I'll skip this. So now, let's assume that the neuron that whose ReLU is switching sides is in the first layer, just for the sake of simplicity. So there is some hyperplane describing where in the input space are the critical points associated with this particular neuron in the first layer. So it's a big hyperplane through the high-dimensional space. And now, suppose that I located one point on that hyperplane, and this is this starting point. And I go in the direction of one of the input coordinates, changing only a particular input coordinate. I'm going to most likely leave the hyperplane where criticality happened with that neuron, because I'm going in a direction which is not following the slope. And then, after I go a short distance away, I try to explore how can I return to criticality, to the critical hyperplane. And I tried in this direction, and either going in this direction or going in the exact opposite direction, I'm forced to hit again the criticality. And therefore, I can measure how far did I go short distance away in one coordinate, and then measure how far did I have to go to return to criticality. And this gives me the ratio between the two coefficients of that linear mapping. So now I can start getting all the ratios between pairs of coefficients in the ReLU that I'm interested in. OK, I hope this is clear how you can find this relationship. Now, you may ask, but you made a simplifying assumption that the criticality happened in the first layer. What happens if in the second layer? Then many things are getting more complicated. I don't have just a simple hyperplane cutting through the whole input space, because it is affected by other ReLU switching elsewhere in different locations. So actually, the hyperplane of the ReLU, the hyperplane of critical points of a ReLU which is deep inside the network, is itself bent in all kinds of directions. But in the local vicinity, it is a simple description. But the bigger question is, how do you know that that critical point belongs to the current layer that I'm investigating? So I have now a full description of all the ratios between pairs of coefficients in the criticality hyperplane of some neuron. I don't know if it is in layer number 7 that I'm now exploring, or in layer number 20, which I'll explore in the future. So how can I tell in which layer it is? So first of all, I know everything that happened in earlier layers. So if I'm now at layer 7, I know all the neurons in previous layers, so I can check if the criticality happened in an earlier layer, because I just calculate what are the values of all the linear of the inputs to ReLUs in the previous layers, and I see if any one of them is 0, then I say, oh, this is well explained. If it's not well explained by the past, then either it is in the current layer or it is in future layers. And here, I'll just give you the basic idea how I distinguish between these two cases, because I want to concentrate my attack only on ReLUs which are in the current layer. If it was in the current layer, then from the point of view of the input, every time I calculate the slope of the hyperplane, but taking into account the input function of the previous I-1 layers, I will get the same slopes, because I see the same hyperplane everywhere, except that it was bent by the known input function, which I take into account. So I'll encounter the slope multiple times in different parts of the input space. On the other hand, if I assume that it is in the current layer, I use what I know about the input function in order to calculate the slopes. But in reality, it is much deeper into the network. What I used as an input function is totally wrong, and therefore I'll not get the same slope a second, a third time, etc. So the rule is every vector of slopes you got multiple times while exploring the network belongs to the current layer. If exploring different parts of the input space, I got a particular slope, but I never saw the same vector of slopes a second time, it belongs to the future. So I have an easy way how to distinguish between these two cases. Next. You know what, I'll skip this because I'm starting to run short of time. So this part is talking about how do I know, OK, I found the slope of critical points where the value is exactly 0. But I have to know whether I'm now, which side of this hyperplane is the positive side of the ReLU and which one is the negative side of the ReLU, because they behave differently. And in order to be able to continue working with later layers, I have to know whether I'm on the negative or positive side. They represent different linear mappings. So there is a way how to take a particular neuron deep in the network and create a movement in input space, kind of wiggle in the input space, small movement in a particular direction in the input space that is going to excite this neuron very, very strongly. It will vibrate like crazy, while all the other neurons are going to be very gently undulating and changing. So forget about this technicality. I have a way how to cause this neuron to vibrate very strongly. And now, what happens is, it is followed by a ReLU. If the output of this was, for example, -3, and I'm vibrating it strongly, there is a ReLU coming afterwards. So all my vibration around a negative point are going to be blocked by the ReLU, because the ReLU is going to make every negative number into a 0. So I'll not be vibrating at all if I was vibrating around a negative value. If I was vibrating around the value of +3 rather than -3, all the vibration is going to be passed on, and it will affect the rest of the network, including the output, and therefore I'll see big wiggles in the output value. So that's the basic idea how I find out the signs. Okay, I'll get to the last part. The last part of the talk is about very recent developments. So after I presented this paper last year, somebody asked me during a presentation, but what happens if you are not given access to the numeric values of the outputs? What happens if you are only given the classification that was produced by the deep neural network? So the deep neural network is a classifier. It has to distinguish between dogs and cars, for example. And it doesn't give you that the probability that it's a dog is 70% and probability that it's a car is 30%. Instead, it just tells you, I think this image is more likely to be a dog. And for another image, it says, I think that it's more likely to be a cat. Can you still recover all the parameters of the network just from the label that it provides to the images? This is the hardest kind of scenario. And the answer that we found after working very hard last year was that it is possible. Even though you get one bit of information for each input, whether it's a dog or a cat, I can use it in order to extract all the parameters in polynomial time. And I'll use the last 3 minutes in order to give you the basic idea of how we do it. So first of all, you have to realize that without access to numeric values at the output, I lost most of my tools. I was using the slope of the output function, where did it bend. Now I don't get it anymore. The probability that it's a cat might have been going slowly and then going down rapidly. I don't sense it because it was a cat. I get the same answer all the time without knowing where the bends are. Okay, so here is the basic mental image you should have in this situation. My input space is still divided into cells. In each cell, you have linear behavior. Now, earlier, we were able to locate the critical points, changing from one linear behavior to another linear behavior by looking at slopes. Instead, what we have now is something which seems to be unrelated, and this is the decision boundary between a dog and a car. So everything on this side of the decision boundary, the network is going to say, I think the image was a dog. Everything on this side, it will say, I think the image was a car. Okay? And now, what is going to happen is that if you are starting at an image of a dog and walking in a straight line to an image of a car, I'm going to encounter the critical points that I encountered before, but I'm not aware of it. Because before I'm getting the information, it's a dog, 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 dog. It's only when I'm crossing the decision boundary that suddenly the network starts telling me a different thing. I think it's actually more likely to be a car. But this point on the decision boundary is not a critical point. It's not a point at which any neuron was switching, any ReLU was switching from positive to negative side. Okay? So I lost this ability to find out critical points. So here is the big idea that enabled us to finish the attack, even in this hardest label-only case. So we define the special case of dual points. A dual point is simultaneously a decision point and a critical point. So if I go back to this picture, you see all these dotted lines are decision points only. Here is both a decision point and a critical point. It's critical because it passes through this line, and it is decision because this is the decision boundary. Okay? So I'm going to concentrate on those dual points, and dual points are critical points, so I can get information out of it. So dual points are the intersection of a d-1 dimensional critical, locally linear hyperplane, and a d-1 dimensional decision boundary, which is d-1 dimensional hyperplane. The intersection of two d-1 dimensional hyperplane in d-dimensional space is d-2 dimensional. Okay? And they leak internal ReLU information. So here's the basic idea of the attack, and this will be the last point I'm going to make. So this is the decision boundary. I started at the image of the dog, and I go towards an image of a car. And I explore the line between them, and the only thing I learn is that when I got to this point in my journey, this is not a dual point, because it's not a critical point. The critical points are only those lines. It is a decision point. Okay, but I know that it's a decision point. I go in a random direction, leaving the decision boundary, and I get to the point x3. I ask the network, what is this? And because it is on the dog side of the decision boundary, I get the answer, it's a dog. So I say, aha, if I'm going to connect this image of that the network thinks is a dog with this image, which is obviously a car, I'm going to cross another time the decision boundary between them. So I found a second point on the decision boundary. I have one point x2 and one point x4, both on the decision boundary. I connect them, and I now can move along the decision boundary. Now I move, and every time I check, am I still on the decision boundary? How do I know? Because moving slightly to this side, it will be a dog. Moving slightly to this side, it's going to be a car. Until I get to a point where going beyond it, I am a car by going both directions. And therefore, I know that it is at this point that the slope of the decision boundary had changed. And it could only be changed by some ReLU switching. So I've finally discovered my critical point, and from there, I'm applying the previous attack. Things are complicated, but I hope you got the basic idea of how such attacks make it quite easy, even if you are only given the final label of the given image to get all the parameters of the deep neural network. Thank you very much.
Thank you, Prof Shamir, for the insightful sharing. Now, let's invite Dr. Zhang Mengmi to moderate the session. Dr. Zhang, please.
Testing. Thank you so much for the very fantastic talk. I enjoyed it a lot. Besides the science, I want to highlight one point that I really appreciate. That is, you can convert math in an intuitive way that all of us understand. Yeah, thank you.
I hope that all of us.
All right. So for the audience, if you have questions, please queue up at the microphone side so that you can start asking questions. Well, I see two gentlemen standing there, so we will start from the one on the left.
Sure. Thank you for the great talk. As far as I understand, this sort of method assumes the architecture of the networks, or is this correct?
Okay. So the way I described it, I assume that the architecture is completely known. You know how many layers there are, how many neurons there are, and so the architecture is completely known. However, it is not difficult to extend it into a situation where you don't know the architecture. Just to give you the sense, when I'm now trying to find all the neurons in the current layer, and I don't know how many are there, I told you about the trick of how to find neurons in the current layer, because I see the same slope occurring in different parts of the input space. So I just generate thousands and thousands of such slopes, and at some point I will not discover any new slope which is occurring more than once. All of them are occurring only once. Then I stop, and by coupon collector, if I've run enough tests, I'm likely to have found all the neurons. So there are ways how to apply the attack even when the architecture is totally unknown.
So you can recover the architecture as well?
Exactly,
okay.
yes.
Thank you.
We'll have the gentleman on the right.
All right, thank you. And thank you so much, Professor Shamir, for the inspiring talk. It's always great to see cryptographic ideas as well in the study of neural networks. So my question is with regards to scaling of some of this analysis. So I think in many of these works, we talk about neural networks. The small neural networks, of course, has nice tractable analytical kind of properties, and it's practical for our students. But we also start to see results of overparameterization, how deep neural networks actually might have different behaviors, and it might even cause some differences in analysis. So my question is actually twofold. First, with regards to your work, how does it scale with regards to deep neural networks, whether the methods and results are the same? And second, especially with regards to how you navigate this and how you might mentor students and mentees with regards to such generalization of problems. We would love to learn from you. Thank you.
So our concrete attack, where we demonstrated that we can run this attack in practice, was with respect to a network of depth 8. In today's world, it's considered quite a shallow network. However, if you think what will go wrong, where am I going to hit a wall, it is only with respect to the accuracy of my calculations. So remember that whenever I'm finding slopes, if I'm using low precision arithmetic, the slope will not be exactly correct. It will be bent slightly. So as you get through more and more layers, errors will start to accumulate. The way we solve it is by using higher precision arithmetic. So in the theoretical model I presented here, I assumed that all numbers are of infinite precision, real numbers with infinite precision, and that in unit time I can add, subtract, multiply, and divide two infinitely precise numbers and get an infinitely precise result. When we attacked the 8-layer network, we used 64-bit arithmetic, and it worked perfectly, no problem at all. I suspect that if we had tried to attack a 100 depth network, we will have to go to a precision, which is double precision, or maybe precision of 1,000 bits or whatever. But if you double your precision, the running time in terms of bit operations only goes quadratically, or slightly less than quadratically. If I want to multiply two n-bit numbers, I don't need more than n-square operations. So it scales very nicely like a quadratic with the precision you need. So as long as you are not doing things crazy, just try high enough precision, and it will cost you 4 times, 8 times more. It will be more expensive, but it will work.
Thank you.
All right, we'll have the gentleman on the left.
So I have a question about the time complexity of your approach. So for the hard boundary systems where there's no numerical output, which strikes me as most useful neural networks available to the consumer today, you said that it required polynomial questions, but exponential time to solve. So for something really complex like ChatGPT, is your solution actually applicable, or would it take too long to compute?
So ChatGPT is way too complicated for us. because, first of all, it has a much deeper network. And in addition, it doesn't have the simple architecture of fully connected deep neural network. It has transformer architecture, and there are all kinds of additional complications in between. So take my attack with a grain of salt when you try to apply it to state-of-the-art models. I don't think that with the resources available to me at the Weizmann Institute, I will be able to recover the parameters of ChatGPT.
Thank you.
All right.
Thank you. I had a question. I think you're highlighting a security issue with neural networks that are developed today. What ideas do you think that you could implement into neural networks that are able to maybe encrypt these nodes to not have somebody be able to get the information?
Excellent question. And the answer I gave last year when I presented this result at a conference was, the paper I presented was with the numeric outputs. I said, I have a wonderful remedy for the problem. Don't release the numeric outputs. Release only the label of the output. And it was then that somebody raised his hand and said, but maybe you can recover the network given only the labels. And then when we worked on it, we discovered it's not such a great idea to remedy the situation. So one thing that is going to kill our approach is if instead of using a ReLU, you use, for example, a sigmoid function. A sigmoid function smoothly changes, has no kinks in it. And therefore, if the ReLU is replaced by something with like sigmoid, then I will not find anywhere a sharp kink in the behavior of the output, and the whole approach will fall down. So there are ways how to avoid it. However, people are using ReLU all the time because it's so nice. It gives you such great results, easy to train, etc. People don't like so much the sigmoid. But if you're worried about protecting against our attack, perhaps replacing ReLU with sigmoid is a good idea. Until someone publishes the next paper in the series showing how to break sigmoid.
All right, the gentleman on the left.
Thanks for the talk. I had a question regarding the hard label case where you mentioned that the tax requires polynomial number of queries, but exponential computation.
No. It requires polynomial. The earlier paper, which appeared at AsiaCrypt, between our previous paper and our new paper, there was a publication which showed that the hard label case could be done in exponential time. So he described an attack, but it wasn't effective. And we were the first to reduce it to polynomial time. So our attack is fully polynomial time in terms of number of queries and the number of computations.
Okay. And just a follow-up question regarding your suggestion to replace ReLU with sigmoid. So sigmoid doesn't have kinks, as you mentioned, in the full precision case, but we operate in limited precision, so you can still have kinks practically, right? So maybe you can still attack that case.
Yes, but then you'll also stop the attacker from exploring the decision boundary with sufficient precision. If you assume that I'm given only, 16 bits of precision, which many deep neural network computations, they're not using high precision. Then I don't have kinks, I'm going to have discrete points. And working with discrete points is going to be quite problematic in order to explore very precisely how the decision boundary changes in space.
Right, thanks.
Hi, thank you for your talk. So I also had a question about the activation function and sigmoids, but perhaps I can ask another one. So commonly today you also have some randomness during inference by, for example, using dropout or things like that. So do you see your method kind of having some boundary to how certain it can be during dropout situations? Or
Again, excellent idea, except that if you're not careful, it will not work. Suppose that you are in the world where the output was numeric, and you add a random number to the output, which says Gaussian distributed around 0. So usually, because real-life images are labeled with very high confidence level as being either cat or a dog, I'm not too worried about taking the decision that this is 90% a cat and making a small noise, adding a small noise to the confidence level, because now it will vary instead of 90% between 87% and 93% confidence level. The decision whether it's more likely to be a cat or a dog will not change. So you can add the noise to the numeric output, and it looks as if, it seems that it will stop the attack. But I can run every query multiple times. And if you didn't create correlations between your noisy effects, then I ask the first query, and I'm getting that it's 91%. The second query, that it's 88%. I'll run 100 queries and get the distribution of the answers due to the noise, and the average is going to be what I'm going to use. It's just a matter of choosing how many times do you have to ask each query in order to cancel the noise in a sufficiently good way.
All right, makes sense. Thank you.
Okay, we run out of time, unfortunately, so let's end today's plenary lecture. And please, just to summarize, in Prof Shamir's talk, he and his team examined a series of fascinating questions at the intersection of AI and security. And please join me in thanking Professor Shamir, and also thank the audience for active participation. Thank you.